Welcome. Okay, that's great. Give me a thumbs up, give me a like if this feed's looking good to you guys. If you're watching this later, then you're probably not subscribed or you haven't seen that I scheduled this one actually today. I'm going to do some sessions this evening. I'm going to be sort of around till 6 o'clock, okay? I'm not going to be live the whole time, but what I'm going to do is dip in and out. These are some OCR Gateway triple physics higher tier questions for you coming up right now. Later on, I've got some EdXL questions and I've got some EDUCAS questions as well, or WJEC. They would also count for that. If you do WJEC, I don't know if your exam's tomorrow or not, like everyone in England, but can you let me know if it is tomorrow? If it's not tomorrow, let me know when it is and I'll do a live stream as well. Basically, all the people in Wales all study the same board, which is WJEC. I do have AQA in a playlist down below. Okay, so I've got a full paper one playlist for AQA. But what I would suggest is watch the live streams because they're all going to be relevant to all different topics, and there's definitely quite a lot of mechanics questions coming your way. Okay, working with velocity time graphs and things like that. There's electricity questions coming your way, and I'm pretty sure that's in all of the paper ones for all the different specifications. All right, if you're A-level and you're tuning in, then you're probably not going to want to watch this because it's all about GCSE papers, but do check out my other A-level exam playlists and maybe check out what A-level Physics Online are doing because they are doing live streams as well on the run-up to exams. All right, so I'm just going to power through the multiple choice and then I'm going to sort of take a moment to look at any kind of comments you've got. And then I'm going to do the longer written ones, and then I'll leave it. And later on, I'll be back again with some key areas that I think you should probably focus on for this exam coming tomorrow. Okay, and the key areas I have got for you are as follows. That I'm going to do momentum, I'm going to do solving circuit problems, and I'm going to do Boyle's law, and I'm also going to do, if I can remember it, so I'm just sorting out the camera just to make sure it's a nice shot for you all. And the one more I'm going to do is, atomic models and how evidence changes models, okay? So model of the atom, Rutherford scattering, all that kind of jazz. All right, so here we go then, multiple choice. I should rattle through this nice and quickly. Ask questions. If there's more things you want me to go through later, then tell me. But I will stop at the kind of end of this. So this first one is asking you to actually use a formula to calculate the resistance of bulb D. Okay, now this one, you're not told, you're told the formula to use. Resistance is potential difference over current, so you don't have to figure that out. But you're not told the current through bulb D. So the first thing you have to do is figure out the current through bulb D, and you know that in a parallel circuit, current is shared between the branches, so you're told 3 goes this way, so you can figure out that 2 amps goes that way. Then here's the equation, R is V over I. You know it's 12 volts because you know it is a parallel circuit, so you know the voltage here is the same as the voltage across the cell, so you just do 12 divided by 2, and that comes out as C, 6 ohms. Okay, next one. This is about magnetic fields around a current carrying wire. So you use the right-hand grip rule. Okay, you know that there's going to be concentric circles. Which direction are they in? So just deciding between B and D there. Use the right-hand grip rule. Your fingers, when the thumb points the direction of the current, your fingers point the direction of the field. So it's got to be D. Okay, which of the following is not? Now they're quite tricky about using this type of thing, this kind of statement in a multiple choice. Which of the following is not needed to generate AC? So have a little read through. You need a changing magnetic field to do EM induction. You need a coil of wire. You don't need a commutator. So a commutator are these split rings that you use on DC generators and DC motors as well. So that's just kind of in brackets there. Split ring commutator. That's not needed. Do you need a rotating magnet? Yes, you do. Okay, because you need to be something moving inside a coil of wire. Either the coil of wire can rotate or the magnet can rotate, but that's fine. So I guess that's quite a tricky one really in that point. But the point is this point here, AC. Commutators are in DC generators, so you don't need that. Okay, student measures the magnetic field strength around a current carrying conductor at increasing distances, plots the results. So basically, they're inversely proportional to R squared, actually. Okay, it doesn't matter the shape, because you just have to figure out the current in the conductor is decreased and a new graph is plotted. Which is the correct graph? Well, just because you decrease the current isn't going to make it into a linear shape. This is the same, and well, this was magnetic field strength on the y-axis. Okay, so the current is proportional to the magnetic field strength that's induced, so it's going to be this one, D. Okay, so that's that one. Hope that makes sense. Same shape, but lower magnetic field strength. Next one here. Car travels 200 kilometers in 4 hours. So I guess what you can immediately do is calculate its speed. 200 divided by 4 gives you 50 kilometers per hour. Now you're told it doubles the speed, so it's now 100 kilometers per hour. And you're asked, how long does it take to travel 50 kilometers, half an hour? Okay, I hope that makes sense. That's quite a straightforward one, really. Okay, a graduated syringe contains air. It's put in a freezer to cool down. When it's removed, the freezer piston has moved inwards. So this is room temperature. This is it cooled down. So the density of air in the syringe when it's cooled is 2.4 kilograms per meter cubed. What was the density of air at room temperature? So basically, this one was 2.4. Okay, in this case, the volume has doubled. Okay, now density is mass over volume. It's a fixed mass. Okay, so this is my equation I've recalled to solve this problem. It's a fixed mass, so mass hasn't changed, but volume has gone from 2 to 4, so the volume's doubled, so the density has halved. So the answer is B. Okay, moving on. This one is just confusingly set out, I must admit. The body is in equilibrium, and something in equilibrium means there's no resultant force acting on it. Okay, so there's 3 forces acting on it, X, Y, and Z. And all the diagrams look the same except for the arrows. So which diagram represents equilibrium? Think about the idea of the vectors adding together. So if I did this vector, then this vector, then this vector, I get back to the same place. Now, is that true for the other ones? Do this vector, then this vector, and then this vector gets me somewhere over here. So no, this is not equilibrium. This vector, then this vector, then this vector, no, that gets me somewhere, no, sorry, that gets me somewhere over here, so it's not this one. This vector, then this vector, and this vector gets me somewhere over here, so it's not this one. So the answer is A. This is the one in equilibrium. In other words, they sum to 0. Okay, the vectors sum to 0. Quite like this question actually, but I can understand how it's going to spend you a bit of time to figure this one out. A uniform 1 meter rod is pivoted at its center, so this is its pivot. So this is about turning forces and moments. You can see straight away. You're told it's in equilibrium. Now this is the case, this is called the principle of moments. The sum of the anti-clockwise moments equals the sum of the clockwise moments. So you ask for the value of the anti-clockwise moment, and straight away you're like, oh no, I just don't know, I don't know all these distances and everything like this. Now you can actually calculate this by saying, well, this moment plus this moment, remembering a moment is a force times a distance, or do you know what, there's a shortcut, because you can say that the sum of this moment is equal to the sum of this moment, so you can just work out this moment here. Now, you're not told this distance, but you are told it's a 1 meter rod. You are told it's 10 centimeters, 0.1 meters from the end. So you know this distance from the force to the pivot is 0.4. So then you can just do 100 newtons times 0.4 gives you 40 newton meters. So the answer is C. Okay, next one. Again, now they're asking you to use the same skill again. Calculate the power dissipated by resistor R. Straight away I saw power dissipated and I thought, oh, I'll use P equals I squared R. But then I looked through the question and I realized that I'm not given the value of R. So I could go ahead and work out R somehow and everything like that. But to be honest, that's a drag. I don't need to do that because I can just remember that power is also current times voltage. Okay, P is IV. So again, though, I'm not told the current through the resistor. So that's a nuisance. But I'm told the current in the main branch, and I know because I understand my Kirchhoff's laws that in a parallel circuit the current in the main branch is equal to the sum of the other currents. Okay, so in other words, I just need to do 250, take away 1, take away 1.25 to give me 0.25 amps in this branch here, and I know as well as parallel, so I know the voltage across there is the same, so I can just do IB, which is 0.25 times 12, and boom, gives me 3 watts. Okay. Next one here, diagram shows 2 poles of a magnet. X is the position of a wire carrying current perpendicularly into the page. So the current is going into the page here. See, north to south, so the magnetic field is coming across in this direction. Okay, get my left hand ready. Field goes across from north to south. Current into page without changing my field. You can't see, but my thumb is pointing down the way, this way. So the answer is A. Okay, make sure you can do this. Force, field, current. Okay, moving on. Okay, a piece of metal has a volume of this, density is this, what's its mass? So recall the density equation. No marking in this case of getting that because it's just a multiple choice. Rearrange for mass, mass is density times volume. Plug in the numbers. Okay, checking before you do that, just check that you're in kilograms per meter cubed and meters cubed. And I want to make sure you can all do this times 10 to the 3 times 2 times 10 to the minus 5. Okay, you're going to pause later on and rewind if you don't know how to use this times 10 to the key. Okay, that is possibly the most important button on the calculator. It's not the most important button, that's nonsense. And the answer comes out at 0.16. Okay, so just a really useful button. Okay, and you know that's 0.16 kilograms, but that's not one of the options. So which one are you going to choose out of these two? Well, just think, how many times do I need to move my decimal place? It's minus 1 moves, in other words. Okay, so that's C. That is 1.6 times 10 to the minus 1. All right, diagram shows 3 gears. Okay, so these come up in the new OCR Gateway. Okay, which are pretty straightforward questions, I think, really. Okay, you just think about them as being multipliers in the ratio of their diameters or the number of teeth. But it's not asking you about the force this time. Okay, it's asking you about the direction of rotation and the rotations per second. And you're told gear X, that's this big one, is rotated at 1 rotation per second. So basically, what direction is Z going? Z we're talking about, okay, not Y. Which direction is it going and how many rotations per second is it going to do? So let's have a little look. So this is going clockwise. So that means that Y will go anti-clockwise, meaning that Z will go clockwise again. So you need one of the 2 clockwise ones, so it can't be this one. Okay, and then how many rotations per second? Well, let's just think about that in number of teeth. So this is going 20 times. We can ignore this one this time. Okay, this is going 10. So this one goes round twice every time this goes round once, because the teeth always interlock, if you like. So it's got to be D. It's got to be this one here, twice as many as the other one. Okay, so number 13, okay. I'm going to get to some questions just after I finish going through these, so don't sweat it. A car and driver with a total mass of 1,000 is travelling at 20 meters per second. The driver applies the brake and the car comes to a stop in 4 seconds. What's the mean force? So my first thought here is, well, all right, I'm going to apply Newton's second law, F equals ma, but I don't have an acceleration. But I do have a change in velocity, 20 to a stop. So A is delta V over T, 20 over 4. The acceleration is 5 meters per second squared. Now I can go ahead and do the mass times the acceleration I've just calculated to give me 5,000 newtons. Okay, so the answer is B. Okay, the current is in a 12 ohm resistor is 9 amps. How much power is dissipated? So this time I am thinking power loss equals I squared R. 9 amps, 12 ohms, 9 squared times 12 gives me 972. So the answer is B. All right, 15 and the end of the multiple choice. How much work is done on a spring? Spring constant, 16 newtons per meter when it's stretched at 50 centimeters. Now I'm straight away thinking I'm going to use this in equation. So do you know what I'm going to do before I do anything? I'm going to convert to, okay, so straight away I'm going to meters. 0.5 meters is 50 centimeters. And now the elastic strain energy is half K delta X squared. That's one I think you get given. Yeah, you get given that one. You just have to select that from the front. And again, go ahead and type that in, being careful that you're squaring the 0.5, not squaring your answer to the first part. And the answer comes out as 2 joules. All right, that's A. I hope that helps everybody. Let's have a little look through some of just the comments, and then I'm going to crack on with the rest of this. Alfie, this is for OCR Gateway. Okay, now in the description down the playlist, there is a playlist for my AQA paper 1, which you can go and watch. But I would suggest you stick around for the live feeds because I'm going to go through loads of questions, and the problem solving is always the same. So although this isn't for AQA, this is for OCR Gateway, and what's coming up is some EdXL and some Educast stuff. Then it's still going to be really useful to you. Next point, last minute revision advice. So what I'm going to do is a question and answer just at the end of today. So I'm going to go through some questions, then some more questions, then some more questions. Then I'm going to go through some question and answer. Last minute revision advice, what I'd be doing is watching my live feed for a couple of hours this evening and then going ahead and getting a nice relaxed evening, okay, just going over the kind of memory work, making sure you memorize your equations, maybe making sure that you're ready with your your equation flashcards on the way into school tomorrow, just those little key bits that you forget, rather than trying to sweat it all tonight, trying to get around something really complicated tonight. Just go through, make sure you're ready, make sure you're in a good mood, good positive frame of mind, ready for the exam. Okay, going to go through these. I've got a few. I haven't done all of them in this kind of specimen paper, but I've got a few longer written ones rather than multiple choice ones to go through with you. So let's just fire into these. So a depth of 10 meters of water exerts the same amount of pressure as the entire Earth's atmosphere, which is roughly 120 kilometers thick. Well, suggest why. Okay, that's the command word, and as you read, I've underlined the command words because that's going to tell you what you're going to do. So this is not something you need to remember, this is something you need to figure out. Well, basically, this is because the density of the water is much, much greater than the density of air. Okay, so that's what I've written there. You could write that in words, obviously. Next one, use the data to describe the relationship between the depth of water and the pressure. Now, you're probably going to know this anyway, so pressure increases as depth increases, and actually that gets you a mark, but you can tell that from this thing as well. Just describing, so why it is just describing. And actually, each 10 meter pressure increases by the same gap. It always increases by 1 every single gap. Okay, now what you could have said is pressure times height. Pressure is proportional to height, or double the depth, double the increase of pressure. Because why there is pressure at 0 meters is because of atmospheric pressure there. Okay, so that's quite a straightforward one really, if you've just done your revision on the pressure section. Okay, same topic then. A container of vegetable oil has 3 holes in it. The vegetable oil has a density of this. Calculate the change in pressure from A to B. Okay, so you need to look at the change in depth from A to B. You're told that B is at 8 centimeters and A is at 12. So the change in depth is 0.04 meters. And that's my standard kind of procedure, convert to meters nice and early. Because actually, in this case, there was a mark for having converted to meters and then going ahead and using that in the equation. So then you need to remember that density is pressure is depth times density times gravitational acceleration, and plug in all those numbers here. Now this is the density that I've been given. Okay, this is the depth I've just worked out, and this is G. And you've got to remember G, although in AQA I know they like you to use 9.81. Okay, and that's absolutely fine. Almost all exam boards really will accept 10 or 9.8 or 9.81. It's up to you what you use, but in OCR you just need to remember it's 10. And the final answer comes out at 364 pascals. So for recall and selecting the equation, converting to meters, calculation, remembering G, and input and calculation for the 4th mark there. Okay, next one. Now we're back on to some circuit problems, okay? A student takes voltage and current measurements for 4 resistors. The table shows the results from this experiment. Okay, which 2 resistors have the same resistance value? So you basically need to work out the resistance of each of these and say which are the same. And that's nice and easy. You just remember that Ohm's law, V equals IR, rearrange for R, R is V equals V over I. Okay, so you need to make sure you memorize your equations, otherwise you've got no chance of getting these 2. So which one's got the same resistance? So I've just shown them here, A 12 over 2, 6, B 6 over 1.5, and lots of people will do these just here, which is absolutely fine. I don't know why they've graded these out in this case. C was 7.5 over 1.5, which is 5, and D was 8 over 2, which is 4 as well. So that's nice and easy. Don't forget to sum this up. So you've shown it with the data and you've stated what that is. Okay, what's the maximum resistance that can be made using these 4 resistors? Well, you can plug them together in series, and then the rule for resistors in series is that basically the total resistance is the sum of all the other resistances. So that just comes out at 19, so just 1 mark, nice and easy. Okay, describe the readings you take. Basically, describe how to do a Ohm's law practical or a VI characteristics practical with the filament bulb. So here's where you just need to remember basically a method. Describe. Draw a circuit and describe. So if you really should be able to do this type of thing here now. There's lots of these questions. Something like this is going to come up. The marks are for... thanks for pointing that out, Laura. Thank you. I'll go back and check that in a minute. That was at the last mark. Yeah, that was the last marking point. Okay, 0 to 12 volt power pack here. Okay, ammeter in series with it and voltmeter in parallel. And lastly, vary the setting on the power pack from 0 to 12. Record the current from the ammeter and the PD from the voltmeter each setting. So remember, diagram, things in the right place, what you're going to measure and why. Okay, you're going to vary it and what you're going to measure it. Right, so this is sketch the shape of the graph you'd expect for that bulb. Okay, remember this, always check the axes labels before you do anything with a graph, because most of you are going to remember this kind of shape of graph, I'm sure, okay, for your VI characteristics of a bulb. So this would be V and this would be I. So actually, they've given you V on the y-axis. So you need to make sure that your gradient increases in this case. So there is just actually one mark for doing that. And then state how this graph can be used to calculate the resistance at any given specific value, where you'd need to use a tangent to the curve at any point. Okay, so in other words, you draw a tangent to the curve at any point and you calculate the gradient of that. So really we're looking at the gradient of the curve at that point. Now how do you know that? Because R is V over I, and that means the rise over the run basically, so that's a gradient. Okay, there's an error with this meter. What's the error called? Well, you're told somewhere that it's not connected, okay? The voltmeter is not connected and not recording a voltage, but it does read a volt. In fact, it reads 1 volt exactly. So that's called a zero error. And the way you deal with that, you can actually change it. That's a little dial that you can change it back to 0. But the way that you can do that is just subtract 1 volt from each reading taken with this meter. Okay, next one. Write down the name of the rule which can be used to predict the direction of the force perpendicular to a current carrying conductor in a magnetic field. That's Fleming's left-hand rule. Just make sure you learn that. You can write left-hand rule. You don't have to write Fleming if you don't want. Use the data to show that why a D experiences the highest force. So this is a similar little question to one of the previous ones. You had to go through and just remember that you can select that from the data sheet. Force is magnetic field strength times current times length, or magnetic flux density times current times length. And so that's basically, this is B, this is I, and this is L. So you just need to do the product of each of these rows. Okay, and I've done that down here. And D is the largest one there. Okay, so moving on. A student decides to build a step-up transformer. Okay, the transformer doubles the input voltage, so that's what we're after. Okay, now there's a key word there. If we're told something like double, make sure we get a factor of 2 somewhere in our answer. Okay, the transformer is a step-up one. Describe how they could build this step-up transformer in a science lab. Right now, actually, I would think, I'm surprised in a way it hasn't said you can draw a diagram, draw and label a diagram, because my first thing is, well, describe how it's built, then I'm blooming well going to draw and label a diagram. So here's my little diagram of a transformer, and I've labelled all the points. Really, most of the marks I could get from this. Basically, this is the primary coil, and you see there's less coils on this than there is on the secondary coil, because it's a step-up transformer. This is the iron core, okay, that's very necessary. It would work, transformer effect does work without it, but the iron core just kind of magnifies the changing magnetic field in there, primary and secondary side, and this is an alternating current input. But I've put that into words as well because that's clear what they're expecting. Transformers have 2 cords of wire around an iron core. That's the basics. What a transformer is, describe how to build one, you need that bit there. A step-up coil, step-up secondary coil, as it's step-up, a secondary coil must have more coils, and as it's double the voltage, must have double the coils on the secondary. Okay, use an alternating current on the primary coil. Okay, and the last mark was for, okay, so I've got more and I've got double. Okay, so there's the 2 marks in there. Okay, next one. Okay then, so one risk associated with this experiment and how it can be reduced. As it step up, we can produce really high voltages on the secondary, so that's a risk. Okay, how can we reduce that? Well, if we insulate it, we're not going to get connected into the circuit. Okay, or you could say use input voltages of less than 6 volts. And why that? Because we're told it's doubling, and actually sort of 12 to 15 is the limit of kind of safe voltages in a lab. So you just needed to say insulate really, but you could have said less, but if you do say less voltage, then be specific of what voltage you should use. Describe how a microphone works. Okay, so a microphone, basically a sound wave, okay, causes a solenoid to move in a magnetic field, which induces an alternating current signal. Okay, now here's my little tip on microphones or loudspeakers. It's those key points. Sound waves, you could say pressure, high pressure and low pressure regions, causes a solenoid to move in a magnetic field, induces an alternating current signal. If it's a loudspeaker, it's the opposite way around. You have an alternating current signal, makes a solenoid move in a magnetic field, produces a sound wave. Okay. This is one that I really want to go through because this really it's really quite tricky at times. Okay, but really you can definitely get these marks. Okay, if you just understand some key things. This conservation momentum type question. later on in the last section of this evening's live feed. So state the law of conservation of momentum. Basically, momentum before an interaction, a collision or anything is equal to momentum after. So momentum before is equal to momentum afterwards is basically the law of conservation of momentum. It also has a caveat that providing no external forces act. You don't really need to say that at all times. Okay, this is my way to solve this one, okay? Always, I would start every single question with this little bit of algebra here. M1U1 plus M2U2 equals M1V1 plus M2V2. It means the momentum of one thing plus the momentum of the other thing, this is before, because these are the initial velocities, is equal to the momentum of the other thing plus the momentum set of marks for that one. Normally it's for actually calculating and summing a momentum, making before and after equal to each other, rearranging and finding your final answer. Be careful with your negatives here. They are important because velocity is vector, and so therefore so is momentum. Okay, a couple more just to do with you. Okay, this one, I quite like this one. You'll like what I've done with this one. Okay, so use the graph to find the acceleration at 5 seconds. Now, we've actually talked about doing this. Okay, how do we find an acceleration from a velocity time graph? That's my point as well. The first thing you do when you get a graph is you look at the axes labeled and you make sure that you are doing the right thing with the right graph. So you need to find the acceleration, and the acceleration of velocity time graph is the gradient. So you need to take a tangent at 5 seconds. Now the way to do a tangent is this. You find the point that you need to do the tangent and identify a nice even number on your ruler. Okay, line up that, I've used the 15 because it's right there, and then look the same distance either side on your ruler. So I'm going to go 3 centimeters this side and 3 centimeters this side. And now I'm trying to make sure that each of those 3 centimeters either side, I'm the same distance away from the line. So I'm just over one small square away from the line each time. And then, I'm happy with my ruler placing, then I'm going to do my tangent. Okay. Now, what you do then is you go ahead and do a line from that, okay, and do a rise over a run for the gradient, okay, and making sure there's the rise, not just reading that off as 60, which some people will make that mistake. So the rise here was 43, 60 to like 17, and then the run was 10, so 0 to 10. So I've just then put that into my normal equation down here, and boom, 4.3 meters per second. I can't remember the exact range of this. I think it's 4 to 4.5 or something like that. Okay, use the graph to find the distance travelled between 0 and 2.5 seconds. So here's where I thought, I know, I won't use the same graph because I'm going to do the area unders, and it's just going to make going through that look really confused. So here it is. I thought, right, I'm going to do the whole distance under the graph, and I went ahead and I split it into little sections, and then I've done a triangle here, and a trapezium, and a trapezium, and a trapezium, done them all, worked them out, written it all out for you, and then read, hang on a minute, use the graph to find the distance between 0 and 2.5 seconds, so not between all the way to 10 seconds. So what's my key learning point there? What do I need to do, everyone? I need to RTFQ, read the question. Okay, so moving on. So it was just a little triangle at the start, which is a half base times height, which again, they give you a little range. Mine's slightly underestimated because equating that to a triangle means I miss out that little tiny bit there. So mine's the bottom of the acceptable range. I think it was 30 to 35 was the acceptable range of answers for that one. Okay. And then next one, again, I've done this on a different one. Here we go, this is our standard, velocity time graph for a skydiver. If they give you this and they tell you to use ideas about forces, then you are in gold, that's an absolute gold mine really, because you should know this graph really well. They're only going to ask you about X and Y, but I'm going to talk through the graph, just the whole kind of sections really. This initial section, weight is greater than drag, so acceleration. And then you get to terminal velocity, where weight is equal to drag. So no acceleration. Then you suddenly get drag much greater than weight, okay? So you get deceleration, okay, negative change in speed. And then you get drag equal to weight once more at a lower speed, a new and lower terminal velocity. So you should know all that. There's going to be questions basically linking your Newton's law stuff, resultant forces with your velocity time stuff. Okay, so just make sure you can do this. They've only asked you about X and Y. So it's basically a 6 marker they're going to look for really a paragraph on X and a paragraph on Y. So during X, she's accelerating as weight is greater than drag. Okay, so mark for just saying that. As you accelerate, drag increases, so there is a lower resultant force. Okay, at the end of section X, acceleration decreases until weight equals drag and she travels at terminal velocity. So make sure the point, I'm using ideas about forces to explain the motion. I'm not just describing the motion here, I'm using ideas about forces to explain the motion. I'm using basically ideas about resultant force, the different forces involved in this to explain the motion. In part Y, she rapidly decelerates as drag is greater than weight. I could have said much greater than weight, but that's what we really need there. This is area causing a large resultant force. Her speed decreases again until drag is equal to weight, and she has a new and lower terminal velocity. Okay, I hope sense. That's kind of 6 marker quality written communication type 1, where you just got to, before you write, when you do that type of question, do a little plan, just think about one paragraph, then the other, and that's absolutely fine. Okay, now if there's any questions from this, then I'm going to have a little look through here. Again, yeah, this is not for AQA, but it should be useful for everybody, I think. I'm going to look, because Laura's pointed out that one of the questions I needed to have the right significant figures. Was that question 10? Yeah, I was looking for the last mark, wasn't I? Okay. Oh, yeah, thank you. Yeah, so you're absolutely right here. So double check that. RTFQ, read the question. And so this should be 360. So I was thinking, well, where's that last mark? Okay, so there we go, significant figure. So that's a really important skill. If you see it's 4 marks and you're thinking, well, where's the other mark going to go? Well, there's something else they've told you to do. So really well pointed out there, well noticed. I didn't swear, I used the letter F to let you make up your own mind. I'm glad, yeah, I like that method for drawing a tangent. And you need to be really accurate with your graphs in these new specifications. We're looking for accuracy to half a small square, plotting or take anything like that. This is for higher sets, okay? So this is a higher tier, but most of the questions are on the same on both foundation and higher. If they need foundation, I did some foundation questions yesterday for OCR Gateway. Later on, I'm going to come back and I'm going to do some Edexcel questions next. That's going to be in about 10 or 15 minutes. Okay, so come back to that. And I just want to, I'm going to stop the feed and so that I can write Edexcel GCSE Physics tomorrow, okay? But do come back to that. And after that, I'm going to do some Educast ones, and then I'm going to go through a few things on any, I'm going to go through a few things. Yeah, I've got my England mug actually, just here. And I'm going to do a few things on that I've listed below in the description, and they so far the ideas I'm going to go through are atomic models, how evidence changes models, Boyle's law, so that's pressure and volume equals a constant, momentum, so momentum before equals momentum afterwards, and I did a question just on that in here, and circuit problems and how you can solve them. All right, all you have a tea as well, because if you've been watching for all that, you need a cup of tea as well, and then I'll come back in like 15 minutes and go through some more questions. All right, cheers.